Hey Trig class, let's go over this 8.4 section, trigonometric identities. So this time we're going to look at how to use algebra to simplify trig expressions and to establish identities, which is basically verifying that what we're seeing is true. So in logic, two statements and applying it to algebra, two functions are identical if the functions are equal for all x's, and that's what we're trying to establish here with these trig functions, that the left side and the right side are completely true, always true. Now these are things that you should have seen before, that we should know already, but what this is basically showing on this sheet is that we can show every single trig function in terms of sine and cosine. So tangent can be in terms of sine and cosine, cotangent, cosecant can be in terms of sine, secant can be in terms of cosine. So all of them, all four, can be determined by sine and or cosine. And then this is also just showing cotangent is the reciprocal of tangent. So the Pythagorean identities, again, you're going to need to know these. You're going to need to memorize these. The Pythagorean identities come from the Pythagorean theorem and a combination of that with the unit circle. So if I take the unit circle, right, and stick a point on that unit circle, there's cosine, sine, right? And I could drop a perpendicular straight down to the x-axis from that point, and that would make a 90-degree angle. And then there is the side of length 1 on the unit circle, and this is our angle right here. That's our theta. And because this is the x-coordinate, x is how far we move left or right, so that's the x, so that's cosine. And because this is the y-coordinate, that's how far we move up and down, so that's y. And so we end up with this right triangle where this is the cosine of the angle. Here's our angle. Here is the sine of the angle, and I wrote y here. That should have been cosine. Or sorry, that should have been sine. And then this was 1. And so by the Pythagorean theorem, this side squared plus this side squared is equal to the hypotenuse squared. All right, 1 squared and 1 squared is 1. So there is the Pythagorean identity, why it has the name Pythagorean identity. It comes from just Pythagorean theorem applied to any point on the unit circle. Now, in addition to that, if I were to take the Pythagorean identity and divide through by either one of these, either divide through by sine or divide through by cosine, I'll start off with sine. I'm sorry, I'll start off with cosine. If I divide the left-hand side by cosine squared theta and the right side as well, I end up with sine squared over cosine squared, which is tangent squared, cosine squared divided by itself, which is 1, and then 1 over the cosine is the secant, like we saw right here. So that means that this identity, when I say this, I mean this one right here, comes from that Pythagorean identity. So it is also a Pythagorean identity. It's just we've divided through by cosine. And then likewise, if I went through and I divided through by sine, divide on the left, you also have to divide on the right, I would get sine squared over sine squared is 1. Cosine over sine is cotangent, which is there, cotangent squared, and then 1 over sine. So they're all three called the Pythagorean identities, but one of them is the geometric. It's just straight up from the unit circle. Okay, you can get the others from dividing through. You can also get the others from triangles and trigonometry, but we won't get into that in this video. Even in odd functions, we've talked about that before. Sine, cosecant, tangent, and cotangent are all odd functions, meaning if you negate the angle that we rotate off the positive x-axis, you negate the output. So all of these have negative output of the original function, but cosine and therefore secant are even. So they do not negate the output. I'm not 100% sure why our publisher decided to separate the odds from the evens by wedging the evens right here in the middle. But anyway, I just want you to understand who's odd and who's even. The easiest thing to remember is cosine and secant are even, and the rest are odd. All right, now we're going to simplify trig expressions. So this isn't necessarily showing that they are an identity or verifying an identity, but we do need to simplify trig expressions well into calculus. So these are very important things when we're going to be establishing identities later on. Using this property that we talked about before, that all of the trig functions can be written in terms of sine and cosine, that's going to be important in establishing identities. Multiplying top and bottom, of a fraction by a well-chosen one. A well-chosen one could be sine squared plus cosine squared. It could be cosine over cosine, tangent over tangent. Well-chosen one just means the top and bottom are equal. And so we are multiplying by 1, which keeps the value the same, but it looks different. It's no different than, I got 1/3 and I'll multiply by 4 over 4. That's a well-chosen one, and now I have 4 over 12, right? So if I was adding this to, 1/12 plus 1/3, the purpose of multiplying by this well-chosen one was to get an equivalent expression that I could add to this, that was very similar to that. It's just we're going to be using a different end goal for why we're multiplying by that well-chosen one. But that just means the top and bottom are the same number when we see that well-chosen one phrase. All right, writing sums of trig ratios as a single ratio, that typically just means like get a common denominator and then add those things together. And then factoring, sometimes factoring will lead to simplification. All right, we want to simplify tangent divided by secant by rewriting each trig function in terms of sine and cosine. That's one thing we're going to do. All right, so let's start that process. Tangent is sine over cosine. Secant is 1 over cosine. So we're going to switch those. And then because we're dividing fractions, we're going to flip the bottom one and multiply. That's just how we divide fractions. The cosines cancel, and we're left with just sine. All right, now let's show that sine divided by 1 minus cosine is the same thing as 1 plus cosine divided by sine. And we're going to do that by multiplying the numerator and denominator of this left-hand side, the sine theta over 1 minus cosine theta by 1 plus cosine. So multiplying top and bottom, this is the well-chosen one. All right, why is this a technique? Well, when I see addition and or subtraction, so in this case subtraction, if I see a subtraction in the denominator, then one thing that we can use there is to multiply by the conjugate. And the conjugate means keep the first and second number the same, just change the sign in the middle to its opposite. So minus becomes plus here. All right, so we're going to multiply top and bottom by 1 plus cosine. On the bottom, because that's a difference of squares, 1 minus cosine times 1 plus cosine is 1 minus cosine squared. Okay, that's just difference of squares formula. Convince yourself by doing it with just general a minus b, a plus b, and foiling it, a times a squared. Outside is a plus b, inside is negative a plus b. So they're going to cancel, and then last is negative b times positive b, which is minus b squared. So you end up with the square of the first times the square of the first minus the square of the second, and that's what's going on in that denominator. All right, 1 minus sine squared, 1 minus cosine squared, that is sine squared. That just comes from the Pythagorean identity. It says sine squared plus cosine squared is equal to 1. So if I subtract cosine squared from that, I would get sine squared equals 1 minus cosine squared. So that's what we're doing right there. And then one sign in the top will reduce with one of the two signs in the bottom, and that leaves us with our expression that we're after, the 1 plus cosine over sine. All right, see as is simplify. Cosine squared theta minus 1 over tangent times cosine plus tangent. And we're going to factor that. So when I see the common term in two different terms, in one it's being multiplied by something, and the other it's maybe being multiplied by a number or something else. But if I see a greatest common factor I can factor out, that's typically a giveaway that I'm going to factor. If I see a difference of squares or some other factoring technique that you saw in like a pre-calculus course, that usually indicates that you're going to factor. All right, so the top is the difference of squares, so that's going to be cosine plus 1, cosine minus 1. The bottom, I pull out that tangent that's common, and I have a cosine plus 1. So notice cosines plus 1s are going to cancel, and that's going to leave me with just cosine theta minus 1 over tangent. All right, and finally we want to simplify 1 plus sine over sine, cotangent minus cosine over cosine, by getting a single ratio. Again, that's just a common denominators, and combine those fractions. So the common denominator here is going to be sine times cosine. So we're going to need to multiply the first fraction by cosine, the second fraction by sine. All right, so left one gets multiplied by cosine over cosine. Again, that's that well-chosen one that it referred to. Second one gets multiplied by sine over sine, and that gives us that common denominator of sine cosine. And then all of this and the numerators can be combined together with just that plus. Okay, so all this just becomes a single fraction with that as its common denominator. So notice what we got here. This cosine, because this is a sum and we're multiplying it by cosine, we've distributed through here. Cosine times 1 is this cosine, cosine times sine. Right here, same thing, we got a parentheses to distribute this sine through. This is sine times cotangent. This is sine times cosine. And notice right here, we got a positive sine cosine. We've got a negative sine cosine. Those are going to cancel. And then on the next line, we just have the cosine, the cotangent times the sine. And then what we're going to do here is just going to rewrite cotangent in terms of sine and cosine. Anytime you're stuck, that's one of your go-tos. You should always just change everything to sine and cosine and see if that helps. Alright, so right here, the sine and the sine in the numerator and the sine in the denominator will cancel. That'll leave us with a cosine plus a cosine, and then that's 2 cosines. Alright, notice now we got a cosine in the numerator, cosine in the denominator. We can cancel that and leave us with 2 over sine, which is cosecant. So that's the idea of simplifying trig expressions. Come up with a way to write it in an easier form than what we started with. Okay, now we need to be able to do that to establish identities. So when I'm establishing an identity, one of the things you cannot do to establish an identity is to multiply both sides of an equation by the same thing. What I mean by that is, let's write these like the strategy that you see to use here is to change everything in terms of sine and cosine, which is a very wise choice. But what I can't do is I cannot multiply both sides of an identity that I'm supposed to establish by the same thing. You know, that cancels, that cancels, that cancels, and I end up with 1 equals 1, which is true. And so, you know, I verified the identity. That absolutely cannot do that. The reason is because when we do this, when we multiply both sides of an equation by the same thing, it's under the assumption that this is true to begin with. And when I establish an identity, I can't assume that it is true. I'm showing that it is true. So you absolutely cannot do that as your procedure, okay? You can never multiply both sides by the same thing, add the same thing to both sides. Anything you do to like solve an algebraic equation, you actually can't do here because you have to work with one side at a time and show you can get the other side. Okay, you can't do the same thing to both, because that makes the assumption that it's true. So we're going to start with the left side. It doesn't really matter which side you start with, but usually you would start with the side that has more stuff to work with. Okay, so the more complicated expression. All right, I'm switching cosecant to 1 over sine. I'm switching tangent to sine over cosine. The sines cancel. It leaves me with 1 over cosine, and 1 over cosine is the secant. And I've established that I can get the right side from the left side without doing anything to both sides. Okay, so this is the left. All right, I'm just doing stuff to the left side and showing that eventually I can get to the right side. All right, that's the idea. That's how we establish an identity. Sometimes this is going to be called verify an identity. Verifying just means show that it's true. And again, we can only work with one side at a time. All right, I got sine squared something plus cosine squared something equals 1. On the left-hand side, I have negative angles on the inside, so I would use that as my starting point because that looks like the even and odd identities. So sine of negative theta is the same thing as the negative of the sine of theta, and the cosine of negative theta is the same thing as just the cosine of theta. All right, but because we are squaring them, negative sine times negative sine is the same thing as positive sine. It would be the same thing as negative 3 times negative 3 is 9. Well, so is positive 3 times positive 3. So I can just drop the negative because I'm squaring. And then sine squared plus cosine squared is the Pythagorean identity. All right, so how could I show that this is a true statement? Well, same thing. I'm going to use those odd properties. There's a whole lot more stuff on the left, and I see those negative thetas, so that's telling me use the odd properties of sine and cosine again. So we already know what the top one's going to do. We're going to get a negative sine, a positive cosine, and on the bottom we're going to have a negative sine and a positive cosine. All right, squaring the sine, squaring the cosine, it's going to give me that. I can write that as a difference of squares. So that'll be sine minus cosine, sine plus cosine. And on the bottom, I can factor out that negative. All right, again, that's a very common thing to do. And then we're just going to cancel the sine plus cosine that's in the numerator and denominator, leaving us with negative. Notice there's a negative down here, and a sine cosine over this negative 1. So the little unseen step here in the PowerPoint is when this cancels, this sine and this sine plus cosine, this sine plus cosine, there's a negative out front, so that leaves a negative 1. So dividing by a negative 1 divides each part. So this becomes a negative sine. This becomes a negative cosine divided by negative 1 becomes a plus cosine. All right, and then they're just bringing the positive cosine in front of the minus sign for that last step. All right, a couple ways you go about this one. I got 1 plus tangent over 1 plus cotangent. And I'm trying to show that's just tangent. So I could change everything in terms of sine and cosine. That's always a way to go. But I could also use the fact that tangent and cotangent are reciprocals. And on the right hand side, I'm left with tangent. So instead of writing tangent as 1 over cotangent, it's smarter here to write the bottom 1 plus cotangent as 1 over tangent. So I'm basically replacing this cotangent with 1 over tangent. All right, now on that, in this fraction right here, just to the side, so you can see where this next step is coming from, I'm just getting a common denominator. The common denominator is tangent. So if I write that 1, this 1 right here, I'm replacing it with tangent over tangent plus 1 over tangent. All right, now I have a common denominator, so that is just tangent and then tangent plus 1. All right, so that whole denominator simplifies to tangent plus 1 over tangent. And then because I'm dividing by a fraction, I can flip and multiply. So you can see what I'm doing here. Again, this kind of step is left out. It's 1 plus tangent u is what's here. And then if we flip this and multiply, I would have tangent, the tangent u that was on the bottom here is now on the top, divided by tangent u plus 1. All right, so I'm just flipping this denominator and multiplying, just like you do when you divide fractions in general. But now the tangent u plus 1 can cancel, and that leaves me with just tangent like we were supposed to show. All right, so left side, we did stuff to it, we ended up with the right side. That's how you establish an identity. You never do anything to both sides. You just manipulate one side and show you can get the other side. I do want you to see there's not one way to do this. So I could have also written this as 1 plus, instead of tangent, I could have said that's sine u over cosine. And on the bottom, that's 1 plus cotangent is cosine over sine. And if I multiply both of these by cosine u, sine u, cosine u, sine u, so I'm distributing this through, this is going to give me cosine u, sine u, plus, when I multiply this one, the cosines will cancel and leave me with a sine squared. All right, on the bottom, if I distribute through, I'd have a cosine u, sine u. And when I distribute through this time, the sines will cancel and leave me with a cosine times cosine. All right, up top, we got a common sine that we can factor out. So that's a sine u comes out, and I'm left with cosine u plus sine u. On the bottom, cosine factors out, and I'm left with sine plus cosine. All right, but these are, because they're adding, they're the same, so I can cancel them out. I'm with the sine over cosine, and sine over cosine is tangent. So again, there's not one way to do these problems. Okay, there is probably a most efficient way, but that doesn't matter. As long as you establish the identity, as long as you start with the left and make your way to the right, then you've done it. All right, we got this expression. We want to show we can get to 2 cosecant. So obviously we're going to start with the left side because it's got more stuff to work with. So we want to get, to start with that left-hand side, we want to get common denominators. So this times sine will be the common denominator. Here, I need to multiply by a sine to get the common denominator. Here, I need to multiply top and bottom by a 1 plus cosine to get the common denominator. So you can see there, I'm going to get the sine squared plus a 1 plus cosine in the parentheses squared over that common denominator. Now, expand this. All right, why would I want to expand that? Well, I have a sine squared, there's a 1, there's a cosine that's going to be squared. This stuff in the numerator is looking a lot like the Pythagorean identity, and if I expand it, I'll have some more stuff to work with. So expanding that, 1 plus cosine times itself will give me a 1. Again, you have to FOIL it out. So 1 times 1 is 1. Outside is cosine. Inside is also cosine. So that's 2 cosine. And then last is cosine squared. So that's where all this is coming from. It's just that 1 plus cosine in the parentheses all squared. And notice here I got a sine squared, a cosine squared, that's equal to 1. These will combine to 1. So we got a 1 there, we got a 1 there. That's going to be 2 plus 2 cosine. And then we're just going to factor out this common 2. That's going to give me 2 times 1 plus cosine, which is in the denominator. That gives me 2 over sine. All right, 2 over sine is 2 times cosecant. And there we've established the identity. So sometimes it takes a little bit to get there. That was a lot of steps to establish that identity, but we never did anything to the left and right sides at the same time. All right, here we want to show that we can get 1 from that expression on the left, meaning that it's just the number 1. A very ugly way to write the number 1. So again, I see tangent, cotangent, secant, cosecant. I'm going to switch things to sines and cosines when I see all of that. So tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, cosecant is 1 over sine. So we've switched things to sines and cosines. Now we're going to get a common denominator in this numerator. So the common denominator here is cosine times sine. So you can see that's what we have here. To get this to have a sine times the cosine, we need to multiply top and bottom by sine. To get this one to have a sine cosine, we need to multiply the top and bottom by cosine. And so you can see that's where the sine squared is coming from and cosine squared. All right, sine squared plus cosine squared is 1. That's the Pythagorean identity. And then because we're dividing by a fraction, we flip, we multiply, all this stuff is going to cancel, and that just leaves us with 1. All right, so in this expression, I see 1 minus sine, I see cosine on the right, 1 plus sine on the bottom. So in this case, we could multiply, it's either or. We could start with the left because they're virtually the same as far as who's more complex. We could multiply the left side by the conjugate of the numerator, or we can multiply the right side by the conjugate of the denominator. It doesn't really matter because they're such similar expressions. But I'm just going to just arbitrarily do the left-hand side and multiply the top and bottom by the conjugate of the numerator. All right, again, when you do that, you're going to get take the negative version, square this, square this. That's what happens when you multiply conjugates. On the denominator, I'm just leaving it in that form for right now. That way when I rewrite this 1 minus cosine squared as, 1 minus sine squared as cosine squared, I can just cancel a cosine in the bottom with a cosine up top. Okay, that's what you want to kind of hold these factored forms when you multiply by conjugates like this for as long as you can. You don't want to avoid distributing through unless you absolutely have to. All right, that's cosine over 1 plus sine, which is what we were told to establish. So that is the right-hand side there. All right, even though it's not universal, it's just about universal to start with the more complicated expression. We have more stuff to work with is what I think of when I see more complicated. Sums or differences of quotients as a single quotient. Again, that's common denominators. Sines and cosines. Just, we have four other trig functions. They can all be written as sines and cosines. So a lot of times when we're stuck, that's the best way to get unstuck, is to get everything to be the same. All right, and this one, always keeping the goal in mind. That's like when we were on this example and I talked about I could write tangent as 1 over cotangent, which is true. Even though that's true, and that would give me something to work with, and I could get to an equivalent, as a simpler expression by doing that, the goal was tangent. So even though I could have done that, it makes way more sense to switch this one to 1 over tangent because it brings another tangent in there rather than getting rid of the thing that I'm trying to get. So that's what we mean by keeping the goal in mind. What is it that I'm trying to establish? Keep that at the forefront of all the decisions you're making as you're trying to make your way from one side to the other.